Hello, pre-calculus class. In this video, we are going to take a look at logarithmic functions, specifically how to find the equation of logarithmic functions that fit a set of data, or at least a couple of points of data. I'm going to split this up into a couple of different sections. In the first little bit, we will get one equation, just like how do I find an equation, kind of the simplest, easiest way possible. And then after that, I'm going to turn myself loose and really explore the math here, because I think it's really interesting and neat, and it's a chance for me to nerd out, and hopefully maybe a couple of you will come nerd out with me. But yeah, logarithms, right, are functions just like any other function. So we can make exponential functions, a times b to the x. We can make power functions, a times x to the b. Linear functions, right, just a plus bx. Quadratics, ax squared plus bx plus c. Logs follow, again, just some basic way, and there's a bunch of different ways you can actually write them. This is just one kind of general equation that we are going to go with for now, that says y equals a plus b times the log base c of x, where your b value is not equal to 0, because then it would just be y equals a. Pretty boring. The c, the base, has to be positive, just like the exponential functions, right? You have to have a positive base for exponential functions. Same thing for logarithmic functions. That base for your log has to be a positive value, otherwise it does not work, right? Explore it in Desmos. You'll get errors or really dotted looking graphs. So the c is 0, c can't be 1, base 1 doesn't really work. Again, kind of the same thing with an exponential function. 1 to any power is just 1. So if this is base 1, it's a very boring little graph. And the x value, the domain here, has to be positive. You cannot put negative things into that, again, for the same reason for exponentials. An exponential function looks like this, and you can't ever have a negative output. Logs are really inverses of exponentials, right? They're going to switch the x and y, and we'll take a look at that in the second half of the video here. But I can't get anything negative out in an exponential function. A logarithmic function looks like this, and I can't put anything negative in to a logarithmic function. So my x value, the domain of this, has to be positive. There are some different characteristics of the graph depending on what your c value is. If c is between 0 and 1, it's actually a decreasing logarithmic function, which is kind of a weird looking graph there. It kind of goes like this. And if c is positive, it's an increasing, or if it's greater than 1, sorry, it's an increasing logarithmic function. But we are going to now take a look at, first, that base, this c value, you can really make it be whatever you want, right? You can make it be 10, you can make it be e, you can make it be 3, you can make it be 1/2. I think if this ends up being a negative, that kind of cancels out that inverse operation there. Usually we are going to choose one of the two common bases, right? Base 10 is the common log. When you just see like the log of x with no base specified, that's log base 10. Or base e, the natural log, where it's the ln of x, that natural log of x. So we're going to find the equation of this log function that fits this data here. So one thing you can kind of see right away, this data ends up being a logarithmic function. And I can see that really it's my x's here that are spaced apart multiplicatively. Right? Like they are all, my x's are getting times by 3 every time, and my y's are increasing linearly. They're just going up 1 every time. That is the opposite of what you would see in an exponential function, right? When you first study exponentials, you know that, right, as your step increases by 1, as your x value, your inputs increase by 1, your outputs are getting multiplied by some constant value. You're multiplying by 2 every time to double it, right? Multiplying by 3 every time. Logs are the inverse. Your y's are what step up linearly by 1 every time, or by 2 if your table is spaced a little differently, and your x's are multiplying. So we're going to do the first method here, which is all I'll really require of you, is that you learn how to do at least one of these methods. This first method I call the brute force method, because really what you're trying to do is you're going to fit this data into some specified box, some specified base specifically. So we are going to choose arbitrarily to make my base be 10, or you could make the base be e. The book does that for one of the questions, right? I'll give you solutions in kind of both manners there. And so when I do that, that makes my equation, this a plus b log base c of x, just look like a plus b log. If it's base 10, I don't need to write a base. It's just y equals a plus b log x, right? So there's my kind of general equation with two now unknowns, two constants that I need to solve for. So we are going to take that equation, and just like you did for the linears and the exponentials and the power functions in section 7-2, we are going to pick 2 points and find the a and the b values. So you can pick any 2 points if it's specific data like this. It doesn't really matter the points that you pick. Sometimes in the book it'll say like use the first and last point. If it's actually like specifically the x's are multiplying every single time by the same value, not approximately the same value, but the same value as the y values step up by the same number, it doesn't matter which points you pick, you'll get the same equation every time. But I'm going to pick 2 points. We'll use the first 2. And again, just like the power and exponentials, I think it's easiest to write the larger x value on top. So I'm going to use that point 18, 2 and the point 6, 1, just the first 2 points here. And I'm going to fit them into that y equals a plus b log x, right? Got y equals a plus b log x when I have an x and a y point here. So that first equation, my x value is 18, my y value is 2, so this equation is going to become 2 equals a plus b times the log of 18. And the second equation, my x is 6, my y is 1, so I'll put in 1 for y, equals a plus b times the log of x is 6. All right. So now again, we have 2 equations with 2 unknowns that we need to work to find, like what are the a and the b values. So I've got these 2 equations stacked on top of each other, and I need to figure out how to cancel something. How do I make something go away so that I have, instead of 2 equations with 2 unknowns, create 1 equation with just 1 unknown. Right? When we had the exponentials and power functions, we had to divide them so that the a values went away. When you have a linear equation, you have to subtract the 2 equations. And this really, like the a and the b values are separated by by addition in this case. So to get rid of the a values, I'm going to subtract one equation from the other. So when I do that, I get left with 2 minus 1 is 1. A minus a goes away, right? The a's are going to cancel when I do that. This cancels the a values. And I'm left with b log 18 minus b log 6. B times the log of 18 minus b times the log of 6. So now I have 1 equation with 1 unknown. The only thing I don't know is the b value. So let's do a little finagling to try to solve this. So I have a b in both of these terms. I'm going to factor that out. Right? So leave the 1 on the other side, equals b times the log of 18 minus the log of 6. Right? So I just take the b out of both of these things. If I were to distribute it back through, I'd get that top thing again. right? But this log 18 minus log 6, I can rewrite that. Got b, it's the log of 18 divided by 6 using that quotient property, right? That quotient property from the properties of logs that says if I have, right, the log of x minus the log of y, that's equal to the log of x divided by y. So I could just rewrite that as 1, and now what's 18 divided by 6? I got 1 equals b times the log of 3. To get b by itself, I divide both sides by the log of 3, so I get 1 over the log of 3 is my b value. All right, you can put that into a calculator, and you'll find that it's approximately like 2.096 is your b value in this general equation, y equals a plus b log x. Right? So now I know one of the two things, I just need to find the other. So I'm going to plug that b back into an equation above and find a. Right. So I'm going to plug in the exact value for that b value. I'm going to take this, the easiest one I have. I have 1 equals a plus b log 6. So I have 1 equals a plus b times the log of 6. But I'm going to put in, right, that b value is 1 over the log of 3. Right, just replacing the b with that. Right. I can rewrite that. Right, 1 equals a plus, just right, think of this as log 6 divided by 1. Multiply the top, I get the log of 6. And on the bottom is the log of 3. So to get a by itself, I'd have to just subtract this term. Right? 1 minus the log of 6 divided by the log of 3 is equal to the a value. And if I plug this into my calculator, I'll get that a is approximately, it's like negative 0.631. So I have my a value, I have my b value, and so I can take those and plug them into my general equation, y equals a plus b log x. So I have y equals a, negative 0.631, plus b, 2.096, times the log of x. And there you go. You have an equation that fits that data. And just in case you were doubting, there's the Desmos graph that proves it. I've got the table of values in there, and then this 2 point, right? Yeah, I can't actually see all of everything here. Oop. Negative 0.631 plus 2.09. Yeah. Can't actually backspace on this when it's in here, so there, right? It is going through those data points there. So that's the general, how I find an equation. I've got some ugly numbers in here, right? The 0.631 and 2.096, but it worked, right? I kind of fit that round peg into a square hole, if you will. So if you are interested in just the basics, you can tune out here. If you want to take it a little bit further, I'm going to roll. I'm going to actually select all of everything, copy it. I'm going to move over to just kind of this new different location here where we can start from scratch. That I said is one method, right? This kind of brute force method, fitting this data into a base 10 log. It's not really naturally a base 10 log, right? Think of logs and exponentials as being inverses of each other, right? And the bases are essentially the same, right? If this were an exponential function, like kind of flipped the x's and y's here, where your x's were the ones that were stepping up by ones, and your y's were the ones multiplying by 3 every time, the base of that exponential function would naturally be 3, right? And it turns out that you get much, much nicer, cleaner numbers if you do that, right? So I'm going to do a second method here that kind of shows you how you can get a much cleaner answer. And this is kind of what the book does for at least some of the time. So we're going to call this method 2. And I call this maybe the more elegant method. Right. Where I take that same data table. Right. We got the x and the y. 6, 18, 54, 162, 1, 2, 3, and 4. And if I know that this is logarithmic, right, like I've got that stepping pattern, my y's are increasing by 1 every time, as my x's are tripling every time. I know that for this data, the inverse is exponential. Right? So an exponential function is y equals a times b to the x power, right? Like this is my general equation for an exponential. If I know that the inverse of this, right, of this data is exponential, then all I really need to do is switch around the x's and the y's, right? So if I wanted to find the inverse, I flip x and y around. So the inverse of this logarithmic data would actually look like x equals a times b to the y power. So if I want to fit my data to this, I'll get a much nicer, cleaner answer. And it's not just a little bit nicer, like it's a very, very different answer. Right? This only works, just a quick note, this only works if it's like really clean and crisp like this. Right? Don't try this elegant method if you have kind of like random data that's like logarithmic-ish, right? If it's kind of a more real world data. But if it's a nice clean table where like I can see this is tripling exactly every time and this is going up by 1 or up by 2 every single time, you'll get a pretty nice clean answer when you do this. So if I'm trying to fit the data to this, I'm going to do it the exact same way that I did exponentials before. I pick 2 points, plug them into this equation and go. So I'm going to have my x, y pairs and fit it into this data here. So I'll pick point, right, 6, 1 again, well, and 18, 2, larger one on top. This time I'm doing the x first. So the x is here. Well, a times b to the y is 2. X equals a times b to the y. Right? And so I'm going to solve this like I did with my exponentials now, right? Where I have 2 unknowns, a and the b, 2 equations. I divide one by the other, right, to cancel my a value here. And I end up with 18 divided by 6 is 3 equals b squared divided by b is just b. There we go. My base for this exponential naturally is 3. Right? And so now pick an equation. I have 6 equals a times b. but I know what b is. So let's get rid of that. And my a value, divide both sides by 3. I get that 2 equals a. So as an exponential, right, this graph fits the data x equals 2 times 3 to the y power. Okay. Now I'd want to rewrite this in log form because I don't really want to have x's first. I want to have this be like y equals something, so it's in function form. So I can rewrite this, right, in logarithmic form, but to do that, right, it needs to be some base to some power equals something on the other side. So I can't have anything multiplying here. I need to have that that term isolated. So we're going to isolate the 3 to the y term here to get it by itself. So to do that, just divide both sides by 2, right? So I'll get x divided by 2 equals 3 to the y. So now I have some base to some power equals something, and I can rewrite this in log form. Because when you have this, this is synonymous with saying that your exponent is equal to the log base b of that answer there. So my exponent, y, equals the log base 3 of x divided by 2. And there's a much nicer, cleaner answer than this, like negative 0.631 plus 2.096 log x, right? And so if I went up here and graphed that data, y equals log base 3 of x divided by 2 also goes directly through the exact same points. It's a much nicer, cleaner answer, right? So that's what I call the elegant method. Works really well when you have data that's perfectly logarithmic, where the inverse would be perfectly exponential. So, but I'm not done yet. These two things, right, are the exact same. We've kind of seen that, right? Like I know graphically speaking that this y up here is equal to this y down there. You can actually get there, and you can use some kind of intermediate steps to help you get there. And if you do this, it makes the answer to question 3 in the book in your homework, again, to me at least, a math nerd, very fascinating, and I love it. So I'm going to come back up here to use this kind of brute force method, but I'm going to wrinkle it a little bit. So we have, right, our a value and our b value set here. If we use these exact values and do a little bit of rewriting, we can actually get to that other answer and get to some intermediate answers that look a little bit different as well. Okay. So I'm going to do a little dividing here. Right. Little space. If I use the exact b value, right, in the, right, I got y equals a plus b log x. If I use the exact b value, right, then I end up with y equals a, let's leave that approximate, right? It's like negative 0.631 plus the b value I'm going to bring here. My b value was 1 over the log of 3, then times the log of x. Okay. Again, I could rewrite that. We got y equals negative 0.631 plus multiply the 1 and the log x. I just get the log x on top divided by the log of 3. But this is my change of base property, right? That if I have like the log of something divided by the log of something else, I can use that change of base formula to write this as the log base 3 of x. Right? And if I just go quick, right, to kind of show that, right, I have the log base 10 of x divided by the log base 10 of 3 in that other equation, so I can rewrite it as the log base 3 of x there. Right? So that already is a lot cleaner. Instead of having this 2.096 nonsense, I just have it's the log base 3 of x. Let's take it one step further. Right? Let's use that exact same thing, but now also use the exact a value. Right. So I have my a was negative 0.631, but exactly it was 1 minus the log of 6 divided by the log of 3. So let's bring that carefully over here. I have y equals a 1 minus the log of 6 divided by the log of 3 plus log base 3 of x. Right? So it's a plus b log x. I've already used the exact b value to write that. So now we're going to use that exact value for a. Okay. This, again, change of base formula. Log of 6 divided by the log of 3 is going to be 1 minus the log base 3 of 6. And plus the log base 3 of x here. I'm going to do a little rearranging just to kind of switch the order around because I have this negative in front here and I don't like that. So let's write that as 1 plus the log base 3 of x minus the log base 3 of 6. Right? But this is a quotient property, right, that we've already seen kind of from above here. That quotient property, the log of something minus the log of something else, is the log of this divided by that. Well, if I rewrite that, this becomes the log base 3 of the first thing divided by the second thing. Right? Which now I got rid of that negative 0.631 nonsense, right? Like now this is a really nice clean answer as well. It looks very similar to that one there. I have the log base 3, right, but they're still not exactly the same, right? So one last step will help us get to there. This 1, right? That 1 I know is equal to the log base 3 of 3, right? Again, this, the log base 3 of 3, saying, right, the log is the exponent. So what's the exponent in the power of 3? That would give me 3 as an answer. Well, I know 3 to the 1 equals 3. Rewritten in log form, that's this. So let's put that in for 1 here. Right? Then I get y equals the log base 3 of 3 plus the log base 3 of x divided by 6. Two logs added together, I can multiply their arguments and make them 1. Right? Use that product property. So I get the log base 3 of 3 times x over 6. 3x divided by 6, I can cancel the 3 and the 6 to make 1/2. I get y equals the log base 3 of x divided by 2, which is the same thing that we had there. So the last 17 minutes of this video is mostly for me, because I think that it's really interesting that you can do that. And again, if you do this, right, get to the exact a and b values for question number 3 in the homework, yeah, something should really jump out at you. So I'm hoping that at least a couple of you do that. Otherwise, this is good enough. the negative 0.631 plus 2.096 log x, it works, right? Every single one of these works. They're all the exact same. Yeah, I might give some bonus points on an assessment if you kind of can show that you can navigate around through different methods, but yeah. So that is logarithmic functions in a nutshell. How do you find the equation through 2 points or a set of points? Good luck.